pristine one, and this one is showing the with the aluminum doped one. First, if you look on this lattice structure, by doping aluminum, the lattice structure is distorted muchly, but it's one almost showing this pristine titanium oxide lattice structure. So in this case, HOMO -1 and HOMO, there was some electron delocalization on the metal part in here, and these are in the LUMO too. But when I dope aluminum, thus this electron is moved towards the oxide part, and also LUMO it's also been showing the all electron transfer to the LUMO layer. So maybe because of this oxygen, it could introduce a charge transfer in this here. This one is just orbital showing of these two previous one. As shown in the previous slide, this electron in the almost on the localized on the metal part. In the LUMO is metal part with oxide layer, but in this case of doped system, this electron is localized on the metal part also. And this is some kind of other presentation of previous slide. But when I take a dose, it's showing that this one is for pristine and this one is for with the metal dope. In the pristine, it's showing that there are overlap between the Fermi. This is the Fermi level. This were occupied on. There are some metal characteristics, but there are some significant, energy difference in the HOMO -1 and HOMO lower energy state. But when I put the aluminum dope, it's giving it a more continuous, orbital, occupations, and also the overlapping of the unoccupied by electron is higher than the undoped system. And these two, I optimized by using the electric field towards the z direction. Z direction means from here is the metal part to the, metal oxide to the metal directions. In that case, I saw that this one in the undoped system, by applying the electric field, it didn't change the energy level that much. But when in this doping system, it increased the occupation of the unoccupied orbitals with the electrons. Excited electron is much more than compared to this one. So from this dose calculation, I can say that this one is because of doping, under the electric field, it changed the occupation number is huge. So doping change can let the change significantly, but most important result is that doping have to increase the conductivity by minimizing the energy gap and increase the occupation number in the higher steady state. So, but I didn't do much work, so there are some feature work to develop videos and those.
Okay, let's thank Javid for interesting presentation. Questions?
Can I see the supercell model again? A lot of disorder, yeah. So what happened? Do you think it's reasonable? Maybe the number of layers that you have maybe is not large enough, or you see exactly what you want. So you want to have a stable some multiply layer, or you want everything
no, I want a stable one layer, and which will increase the conductivity if I apply the, which will change the resistivity if I apply the current. So that's my.
So you're trying to model more like a thin film, right?
Yeah.
Right. So I would assume that with a thin film you have a multiply region, right? Inside the thin film should be like in a work system, right? And near the surface you may have surface reconstruction, surface relaxation, or whatever, right? So it seems that your system is not, good enough to see that. Another thing that you can do is, in addition to adding some more layer, you fix the middle layer. To add like, 3 layers in the middle, fix them at the bulk largest cost, right? So in order to mimic the bulk layer in the thin film, right?
So my another aim is actually to minimize these device sizes. So if I want to make another layer, it will mimic the bulk sizes, but I want to make a smaller device. I mean 2D device, one layer.
Ah, okay, so you want
So,
a very,
yeah.
very thin.
So
okay.
then I can make a bigger number, many number of devices in small pieces. That's also important.
Have you considered tunneling?
Yeah, I have to. So I cannot make it as more smaller. So that's why I need to optimize.
But is this big enough?
I want to minimize tunneling because if I get the more tunneling, it will become a conductor. So we need to optimize tunneling and Scott cubic barrier too.
Okay, but we should be short.
How do you incorporate electric field into your system?
In bulbs, there have this one, but do you want methodology how to use this one, or
Okay, so
how do
there
you
is
calculate this one?
There's a strict methodology that you have to follow.
Yeah.
Is that in your?
Yeah. No, I didn't include that.
Okay, sounds good.
But I do have. I can if you want.
Okay, let's thank Javid once again. And we have third.
Dimitri, we just received notice, obviously will be closed.
Yes, we will be finished before.
Okay,
before
just
this.
like you know.
But thank you much for bringing this up. So we have 3 presentations more, and the next is by Samuel Brown, who is at the Department of Polymers and Coatings, and he will make another presentation on metal nanoclusters and their optical properties. Floor is yours.
Thanks, Dimitri. As you mentioned, I'll be exploring the oxidation states for optically active silver nanoclusters. So to begin with, I'm just going to describe silver at different length scales. So here you can see we have silver in the bulk, just a silver metal block. And then this, if you look, is a TEM image of a silver nanoparticle that's about 6 nanometers in diameter. And then here's the model that we'll be working with later, a silver nanocluster that's only 13 atoms total. And then here's the representative density of states for each one of these models. So just kind of for reference of what we'll be looking at. So because the density of states becomes discretized for the smaller nanocrystals, that allows for different optical transitions. And then work by Diaz and Ross showed that, one of the papers showed that you can actually get fluorescence from these models. And then with the nanoparticles that are slightly bigger, you can get surface plasmon resonance, which alters the absorbance properties. In this presentation, though, we'll be focusing mainly on the silver nano clusters, the very small ones, that can be optically active. So here's a molecular dynamics room temperature of the model that we'll be going over. So it's a silver nanocluster with 13 atoms making up the core of the silver, and then it's passivated with 12 cytosine molecules. So typically when they synthesize these in the lab, they use DNA as a scaffolding material. So for this case, we're using cytosine as the representative scaffolding.
I interrupt you right away.
Yeah.
Do you know the structure? Is it known experimentally for that it's really 13 atoms in the silver? And also, what's the conformation silver has? Is it experimentally known, or you just took this structure because you need some to
I think
start?
something just to start with.
Okay, so no experimental data on this.
Yeah.
Okay.
So what we wanted to do first was just explore the different oxidation states and charges of the system to see if we can find the lowest energy. And when we did that, we found that the lowest energy was at a charge about -500, which is extremely low. So we decided to kind of explore a different area. So we went and looked at the charges around the neutral state. And looking at this, we can see that we get a deviation from the parabolic function we saw earlier to a quadratic function here with a inflection point around -6. This inflection point doesn't give us a whole lot. I looked at density states around it, and it seems to be similar, but looking at these models, we then explored the band gap for these ones, which is here. So I didn't mention, we looked at different spins of 0, 1, 2, and 3. So this is spin 0, 1, 2, and 3. And then we looked at the band gap for all these different oxidation states. And for high oxidation states from about 3 to 10 in these models, we can see that the band gap considerably widens to about 2 eV. And since we did this for both alpha and beta electrons, we multiplied the band gap of the beta electrons by -1, so that's why we have a negative band gap here. Looking at the models, that were optically active and it had a band gap in the previous one. We plotted the band gap, the HOMO LUMO energy for these different states, which is here. So you can see for higher oxidation states, +11 compared to +5, that both the HOMO and LUMO energy drop, and that's pretty much